Good evening, everyone. Thank you for joining us tonight for this presentation on erosion, corrosion, and material loss, concentrations in pipelines and valves that is brought to you by Erosion Corrosion Research Center at the University of Tulsa and Total Valve Systems. Quick introduction on the speakers. I'm Suri Karimi. I'm an assistant professor of mechanical engineering at the University of Tulsa. I received my PhD from the University of Tulsa in 2018, but I have been here for a long time, since 2014. My research focuses on modeling and experimental investigation of fluid dynamics, particle tracking, durability, and erosion of materials, and renewable energy applications. I am the PI of Einstein Government Research Group and the co-PI of Erosion Corrosion Research Center at the University of Tulsa. And my research is currently supported by OCAS, Schlumberger, and multiple other industry partners. The next speaker is Dr. Enas Nasser. He is an assistant professor of engineering and applied technology at Tulsa Community College and a postdoctoral research associate of Erosion Corrosion Research Center. His research focuses on erosion corrosion mitigation through inhibitors and corrosion-resistant alloys. He received his PhD in mechanical engineering from the University of Tulsa in 2019. He has authored and co-authored many publications on his research. Last but not least is Michael Leiberger. He is the president and owner of the Total Valve Systems and the sponsor for this talk tonight. He has a Bachelor of Science in Aeronautical and Astronautical Engineering from Ohio State, MS in Aerospace Engineering from the University of Cincinnati, and MBA from Vanderbilt University. He holds 12 individual or joint design patents. He was general manager for GE and instructor of Six Sigma. Mike left GE Word and pursued his passion of owning and operating a small family-based company. He is also a pilot and saltwater fisherman. Not two things you think you can go together. So that's cool. So with that being said, this brings me to a little overview of the topic of our talk tonight, which is wear of materials. Wear is the damage to a solid surface, usually involving progressive loss of material due to relative motion between that surface and a contacting substance or substances. And it has four main forms. Abrasion, which is hard, sharp surfaces imposed on softer surfaces. Adhesion, which is interaction between conforming surfaces. Surface fatigue, which is repetitive compressive stresses. And erosion, which requires fluid action, and it is the focus of our talk tonight. But what is erosion? Erosion is progressive loss of material from the solid surface due to mechanical interaction between the surface and the fluid or an impinging stream. Fluids might be multi-component and may contain solid particles. Erosion can also happen concurrently with corrosion, which is chemical reaction with the solid surface. Erosion can happen under different conditions. We have solid particle impingement, when we have continuous succession of impacts from solid particles on the surface. We have fluid impingement, which happens under high velocity, such as in aerospace or turbo machinery. We have cavitation, which is erosion by collapse of bubbles and train in the liquid. And we have slurry erosion, which is a mixture of solid particles and liquids or multi-phase flows. So, as you see, there are multiple conditions that erosion can happen under, so it's important for us to understand this and be able to predict and control it, because it could be damaging, such as the first picture from the top that you see. We have a pump propeller that was navigated by bubbles, or we could use our benefits, such as in the water jet, to cut material. So, that is the fluid impingement. So in this talk, we're going to talk about some of these types of erosion and the research we are doing on them, and how the University of Tulsa is doing some work and what Total Valve is doing on some of these conditions. So let me give you a little background A guideline that was used for many industries, especially oil and gas industries, is the American Petroleum Institute recommended, or API-RP, the Institute recommended practice, API-RP 14E. And it calculates an erosional threshold velocity in pipelines and valves. And as you see, let me see if I can use the pointer here. As you see, there is no specific information on erosivity and corrosivity of the fluid is available. So all we have is the threshold velocity under which you say erosion doesn't happen, right? And the only component, the only parameter we have here is the mixture density. And we have this C constant that is usually 100 for some cases, 120 for some other cases. And if sand is anticipated, then they use some lower values of C. As you see, this equation does not take into account a lot of parameters. There's only density there. So it's not very accurate, although it has been used by industry for many, many years. It does not take into account the flow regime, the material properties, the eroded properties, or anything else that we can think of. Therefore, a lot of researchers started to think about this, and that's the reason that the Erosion Corrosion Research Center at the University of Tulsa started doing research in 1983. That's where it was founded, and it has been a continuous consortium. So ECRC was formed to develop guidelines to replace the API-RP 14E, which is a guideline to just determine erosional velocity. And as I said, it was previously used by oil and gas companies to design bellbores, flow lines, and transportation pipelines. So what ECRC does in our approaches is that we conduct experiments for various parameters, such as we look at geometries, flow regimes, solid particle concentration, and properties such as material, property, size, shape. We look at gas, liquid, and particle velocities, and many other factors. Then we also conduct CFD simulations for different cases to see how well we can predict this type of behavior. Then we validate the models against our experimental data. Then we improve or develop models to predict erosion and corrosion based on the data and our abilities, and we work on them as we gather more data. And finally, we implement all the improved models in ECRC developed software that are actually our product. So let me show you some slides that says how the API-RP practice was not doing a good job in many different cases. Okay? So for example, on this graph, we have erosional velocity on the vertical axis and pressure on the horizontal axis. And the red line shows the API-RP 14E. At ECRC, we developed models to look at droplet models of erosion without particles or when droplets contain particles. And as you see, the API model could not account for liquid droplets or sand. So, and when you look at these models that take that into account, you see how this is diverging from actually what it could be. The other thing, like in this slide, here I'm showing you application of erosion modeling to determine the threshold velocity, like what are my operating conditions. So here I have the superficial liquid velocity and the superficial gas velocity. And as you see here, this API model cannot account for, as it cannot account for sand rate or erosion, and it's very, very conservative, where you could be operating at higher velocities without without getting much erosion. So it's like being conservative and not doing a very good job. That's why we need other models. The next slide shows the liquid rate versus gas rate. Again, here you see the API model that can be very conservative when low or no sand production is in the system compared to this model that we have for low sand that was developed and validated at Erosion Corrosion Research Center. So all in all, you see that practice that is available is not doing a good job. It's not taking into account a lot of patterns. So what we do is that we develop these models and we verify them with the data that we have in the literature, with the data that we gather at ECRC. So for example, this is one of our softwares when we have one-dimensional prediction against the experimental data. This black line shows the perfect agreement, and you see we have multiple experimental data from different researchers in the literature. And we are getting relatively good predictions compared to what API or previous practice was doing. And other example, like API is not the only thing that is out there. Another practice is DNV implemented practice. In this slide, we are looking at the predicted erosion versus the experimental erosion for large-scale erosion tests for stand-up elbows. And the blue dots or symbols shows our software SPPS version 6.2 results compared to DNV results. And you see that our R-squared values are much higher. So we have developed better models and software to predict for these conditions what we see in the experimental data. This is another set of data, but we are looking at CFD versus our software. CFD could be, we do a lot of CFD, but CFD could be time consuming. It could be very expensive, computationally expensive. So our models are going to do this faster and with less computational fees or prices. And here we are looking at the predicted erosion by our models compared to the CFD predictions. And again, you see that our model compared to the DMV is just like much higher R-squared values. So our software is doing a much better job in predicting all these cases. So let me tell you a little bit about the main software that we have. Sand Production Pipe Saver, or SPPS, is a very user-friendly software, and it is Excel-based, and it's available to all our members. I'll talk about that later. But current capabilities include erosion prediction. It's not all this, it's a lot more. Elbows, long radius elbows, tees, straight pipes, direct impingement, sudden expansion geometries, plug tees, gradual and sudden contractions, and in SPPS 2D, we have some other limited geometry with single phase, and then in 1D, we have single phase, multi-phase, and all that stuff. So our software calculates your flow regime and also the erosion that you see based on the input that you would provide it. So I'm just showing you some of the basically window pop-ups of the software, what is available to you. For example, you can choose your geometry from all these options that you have here for the 1D model or the 2D model. And I have some information here that I'm just going to skip over. And then we also have different materials that we have tested. We have different materials we've tested at ECRC. We have some other projects. We have projects for Chevron and some other material that we have tested. And all this data we put into our software so that all of our members can study and investigate and have access to all of our data. Long story short, comparing the presentment and this method, SPPS, and the API or P14E practice, you see we only have fluid density there and we only have the threshold flow velocity. But SPPS is checking all these boxes. We consider flow velocity, flow viscosity, fluid density, stain density, gas and liquid, sand size, sand production, sand sharpness, material type, pipe diameter, flow geometries, all these different geometries, and we can give you impingement velocity, the threshold velocity, the maximum penetration. So compared to the recommended practice that was available, and the industry was using it for a long time, we can provide you a lot more information, and we can consider taking into account a lot more parameters. So with that, I'm going to give it to my colleague to talk about our work on erosion corrosion. Thank you.
Hi everyone, my name is Nco2, and I will be talking about the erosion corrosion studies. Was it? Okay. All right. So I will be talking about the erosion corrosion studies, including the modeling efforts that have been done by the Erosion Corrosion Research Center of the University of Tulsa. This is the outline of my part of the presentation. I will start with erosion corrosion of carbon steel and CO2 corrosion model. Then I will be talking about the effects of inhibitor on erosion corrosion and how can we model the performance of corrosion inhibitors. And for the last part, I will be talking about erosion corrosion of corrosion resistance alloys. So, erosion corrosion of carbon steel. As we all know, in oil and gas industry, carbon steel is used as pipeline and process equipment material because of its availability, low cost, and excellent mechanical properties. However, a negative side of carbon steel material is that it has limited corrosion resistance. And CO2 corrosion is considered as one of the severest forms of corrosion that we can find in oil and gas industry. So, in CO2 corrosion, or when carbon steel is exposed to a brine solution containing CO2 gas, so iron carbonate scale forms over steel surface. So, as we can see here, if the blue color represents carbon steel material, then the brown color represents iron carbonate scale. So, this iron carbonate scale, so just depending on the environmental conditions of temperature, pH, flow velocities, and concentration of species, this iron carbonate scale could form over steel surface. So this iron carbonate scale is protective and can reduce corrosion to lower values. However, the presence of solid particles, as we can see here, can deteriorate the scale, decrease protection, and increase corrosion to unacceptable levels. Under scale-forming environmental conditions, there is always a tendency for scale to reform again, as we can see here, while solid particle erosion is taking place. Therefore, significant synergism between erosion and corrosion can take place. So, when in the cases when corrosion is becoming increasingly high, so chemical inhibitors are commonly utilized to minimize corrosion. And this is going to be the second part of my presentation today, the corrosion inhibitor topic. Right, so the questions that we can ask here. So how can we tell whether my system has a tendency to form a scale? And how can we estimate corrosion rate? So many oil and gas and service companies in the literature have developed models that can predict corrosion rate. ECRC, the Erosion Corrosion Research Center of the University of Tulsa, has also developed a model that can be used to predict CO2 corrosion and the formation of iron carbonate scale. This model is developed based on the mechanism of CO2 corrosion and takes into account the flow velocity, pipe size, the chemistry of the solution, including pH, concentration of species, and such as the carbonate and iron ions. And finally, ECRC have developed a user-friendly computer program based on this model. And here we can see the input stream from the model. So the ECRC model is known as SPPS-CO2. Okay, so as you can see here, so the first column from the left in the program, so it's like has got like a description where we can write a description about the case that we are running, Here we have got the temperature, okay, and there is like a drop down button as you can see here, so where we can switch from SI units to English units and vice versa. Then we have CO2 partial pressure, the pipe diameter, pipe roughness, liquid rate, liquid density, liquid viscosity, gas rate, gas density, gas viscosity, interfacial tension, and here we have the column for pH. And a good feature about this model, even if we don't have like the pH entered in the input screen, so we can, this model can calculate the pH for us based on the CO2 partial pressure and the bicarbonate that is initially added into the system. All right. So here I have got like a couple of cases. Okay. So for low temperature, high temperature cases. So the first three cases we have like low temperature and high temperature. For the high temperature cases, they have like high temperature with no bicarbonate with no bicarbonate initially added into the system, and another high temperature case with bicarbonate initially added into the system. Now we're going to see how this affects the corrosion rate and pH values. We have no pH entered for these cases. Okay, so by hitting the run button here, okay, we're going to get to the output screen from the computer program. So as you can see here, it's showing me the description column again. Then we have like the pH. So the pH is calculated for us. Okay, and as I mentioned earlier, so pH, the value of the pH is depending on the partial pressure of CO2 gas and the concentration of bicarbonate. So for the case here, for the very last case where we have like bicarbonate like initially added, so I have got a pH value higher than the other cases where the bicarbonate was not added into the system. All right. So again, as you can see here, for low, we have like for the output screens also giving me the ion concentrations, corrosion rate, and melt per year, millimeters per year. There's also a column where it says there is a scale or no scale, and also it's also giving me information about the flow path. Okay, so here for the low temperature case, okay, so no scale was predicted. Okay, and for high temperature, as we would expect, there would be a scale. Okay, but how good is the scale? We can do that by the corrosion rate here. So if you look at the two cases here, okay, so we have like two scale for me. Okay, so one, if you look at the corrosion rate, so the one with high pH has lower corrosion than the one with low pH. Okay, so it seems like, or what I can notice here is that higher pH is giving me a scale that is more protective against CO2 corrosion. Okay, and this just depends on like the properties of the scale. So if we have got the scale formed at low temperature, then it's going to be fluffy and soft. If we have got like a scale that is formed at high pH and high temperature, then it's going to be harder and more protective. Okay, we go back to the input screen again. Okay, I have like three cases here done for multi-phase at low temperature. So since it's low temperature, we would expect non-scale forming. Okay, but the I will try to, from these cases, I will try to examine the flow pattern estimation or the flow pattern calculation here. Right. So for the three cases here, I have like low gas flow rate, medium gas flow rate, and high gas flow rate. And again, here from the output screen, for the three cases, since I have low temperature, low pH, so non-scale was predicted, and also I have the corrosion rate value listed for me here. Okay, and depending on the velocity of the gas, I have got different flow paths. So for low gas, I have dispersible bubbly flow, and then for medium gas, I have slug flow, and then for high gas flow rate, I have an annular flow. Okay, so, and this is one of the capabilities of this model. So, one capability that I mentioned earlier is it can calculate the pH, even if we don't enter the pH of my system. And also, it's giving me more information than the corrosion rate estimation, which is the flow pattern. All right, so after looking at how can we reduce corrosion by the presence of iron carbonate scale, now we're going to look at how can we minimize corrosion by adding chemical inhibitors. So as I mentioned earlier, so when corrosion rate is becoming increasingly high, chemical inhibitors are commonly utilized to minimize corrosion. The mechanism of corrosion protection by inhibitors is generally modeled by the physical chemical absorption of the inhibitor molecule to the metal surface. And this absorption phenomena depends on the chemical composition of the inhibitor molecule, the environmental temperature, and the electrochemical potential at the metal solution interface. So many absorption models that have been developed to model the performance of corrosion inhibitors. These models include Fromkin, Temkin, Langmuir, and Fleury-Hagens. All of these models use the general form of equation that is given here, where KD is the adsorption-desorption coefficient, C sub I H is the inhibitor concentration, H is the configurational factor, which is function of theta. Theta is the surface coverage by the inhibitor. N is the ratio of the inhibitor molecule coverage to water molecule coverage. And here we have F, which represents the interaction between adsorbent inhibitor molecules. And based on studies that we have done at the Erosion Corrosion Research Center of the University of Tulsa, we have found that Fromkin adsorption isotherm as a best representative model for studying the performance of corrosion inhibitors in presence of solid particles. So as we can see here, Fromkin isotherm was modified so it accounts for changing temperature and erosion rate. There is also, it's used to develop a relationship between the inhibitor concentration and the surface coverage by the inhibitor theta. The surface coverage by the inhibitor theta is given by one negative inhibited corrosion over uninhibited corrosion. All right. So, Dr. Hassan and co-workers, so a former student at the University of Tulsa, have studied the performance of midazoline-based inhibitor in reducing CO2 corrosion in presence of solid particles. So he conducted a set of inhibited corrosion experiments under lens-scale forming conditions at a temperature of 135 degrees Fahrenheit, at pH of 4.8, 32.63 per second low velocity, 20 psi CO2 gas, in a flow loop with a direct impingement configuration. Okay, so the experimental data collected from these experiments are shown here. So the orange circle data points represents inhibited corrosion experimental data, and the green line represents Fromkin isotherm fit to these inhibited corrosion data. And as we can see here, so the vertical axis represents the inhibitor concentration in ppm, and the vertical axis represents the surface coverage by the inhibitor. So zero, what does zero mean? Zero means no coverage, and corrosion rate is relatively high, and 1 means complete coverage by the inhibitor, and corrosion rate is getting low. So, and as we can see here, there is an exponential relationship between the inhibitor concentration and the surface coverage by the inhibitor. So this was data for for inhibited corrosion in absence of solid particles. Under the same environmental conditions that are discussed here, so Hassani and co-workers at ECRC have conducted inhibited erosion corrosion experiments in a flow loop with a direct impingement configuration. The erosion corrosion experiments were conducted with 0.3% by weight particle sand concentration. And here we can see the inhibited erosion corrosion experimental data in this graph. So the blue square data points represent inhibited erosion corrosion experimental data with 0.3% by weight sand concentration. As mentioned earlier, the green line represents Fromkin isotherm fit to inhibited corrosion with no sand. The red line represents Fromkin isotherm fit to inhibited erosion corrosion with 0.3% by weight sand concentration. By looking at the 25 ppm inhibitor concentration, okay, so the surface coverage by the inhibitor is higher in absence of sand as compared to the surface coverage by the same amount of inhibitor in the presence of sand. sand. Also, by looking at this arrow here, there is a large shift to the right and downward by adding sand into the system. Therefore, adding sand into the system reduces the inhibitor effectiveness in reducing CO2 corrosion of carbon steel material. Alright, so after we look at how can we model the performance of corrosion protection by inhibitor, now we're going to see the performance of corrosion resistance alloys under erosion corrosion conditions. Alright, so corrosion resistance alloys such as stainless steels, nickel alloys, and some titanium alloys are widely used in oil and gas industry. So CRAs depend on a passive oxide film for corrosion resistance. So if the blue color represents the substrate of the corrosion resistance alloy, then the pale blue color represents the oxide layer, or representing the passive film that the CRA uses for its corrosion protection. The presence of solid particles can break the passive film and increase the surface that is exposed to the corrosive environment and can lead to higher corrosion. In presence of oxygen, there is a tendency for the passive layer, or the oxide layer, to have repassivation and reformation again, okay? While solid particle erosion is taking place, which suggests a synergistic effect between erosion and corrosion. In oxygen-free environment, these oxide layers may not reform again. Also in salt water, we can have like two competing processes that is happening at the same time. So the chloride ion can break the passive layer, and then the dissolved oxygen can work on the repassivation. So the question here, is erosion corrosion a serious problem for CRAs in oil and gas industry? And how much is the erosivity of the environment for erosion corrosion needs to be to be a serious problem in CRAs? So Rincon and co-workers at ECRC have tried to address these questions by conducting erosion corrosion experiments on 13 chromium steel in a multi-phase flow conditions. In a flow loop with a direct and minimum geometry, he conducted pure erosion, pure corrosion, and erosion corrosion experiments at a superficial gas velocity of 97 feet per second, superficial liquid velocity of 0.2 feet per second, a temperature of 76 degrees Fahrenheit, a pH of 4, 2% by weight side concentration, and 50 psi CO2 gas. And the results he obtained from these experiments are shown in here. So the vertical axis representing the penetration rate in mils per year. Then the first column from the left represents pure corrosion. Then we have pure erosion, okay? So it's just the solid particle erosion action here. Okay, and then here we have erosion corrosion, the combined effect. So as we can see here, so erosion corrosion does not give exactly the summation of pure erosion and pure corrosion, suggesting a synergistic effect or a synergism between erosion and corrosion for 13 chromium steel under these environmental conditions. Rincon also studied the effect of temperature on the synergism between erosion and corrosion for 13 chromium steel. So he conducted pure erosion and erosion corrosion experiments on 13 chromium steel with sand in a single phase, a flow loop with a direct confinement configuration, with a liquid velocity of 15 feet per second, a pH of 4.4, 2% by weight sand concentration, and 50 psi CO2 gas. And as before, the vertical axis represents penetration rate in mils per year, and the first two columns represent the comparison between pure erosion and erosion corrosion at 70 degrees, then the same comparison from 50, and then a comparison at 200 degree Fahrenheit, okay? So as we can see here, there is like a difference, there is between pure erosion and erosion corrosion, okay, for each of these data, okay, and this difference or the synergism between erosion and corrosion is increasing with increasing temperature. And as for future work and work that is still in progress for the performance of CRAs, we are conducting studies on Nco2 718 and also the diplex stainless steel, the 2507, the alloys that are commonly used in oil and gas industry. All right, so this, now I will turn it over to Mike, and then I will see you back again.
Coupled with the University of Tulsa, Full Valve has been working on understanding erosion corrosion relative to the valve. So it's important to understand that once the scale builds up, whether it's the iron carbonate or it's a non-carbon steel alloy, what can happen when you cycle a valve open and close in the pipeline, right? So that scale goes downstream, and if you leave the valve open, something like this could happen, like cavitation, so you just crack the valve off the seat. You get the flow accelerating through that orifice, if you want to call it that, and you can get cavitation if you just leave the valve off the seat. So again, working with these guys over the last 3 or 4 years, plus some additional research that we've done, we have come up with a method that we're rolling out in 2023. Again, this just goes through some of the cavitation damage, and you'll see some pictures in a minute of what inside of a pipe or valve can look like due to the vapor pressure of the fluid being below the vapor pressure of the fluid of your media being the fluid going through there. I'm sorry, the fluid vapor pressure is lower, and so you get cavitation damage. So this is some of the trim out of the valve. This is a control valve. This is another flashing issue inside a control valve. Again, this if you have it on a seat of a ball valve, which is not in here. So that slide is, we're just going to talk about that slide that's not in here. But again, in the world of ball valves, we've done a lot with trunnion, pipeline, ball valves. And what we have developed is a self-healing system when you do get your seat damage inside a ball valve due to erosion corrosion. It's going to heal itself. You can flush it out with a flush and put this self-healing system in the valve to seal it. So back to the University of Tulsa.
So some capabilities of University of Tulsa and Total Lab, we're going to talk about this. So we have 2 main groups, Erosion Corrosion Research Center and Tulsa University Senior Management Project, or TUSMP. Our capabilities go to 2 main categories: experimental facilities and modeling capabilities and software. So I'm going to go over those pretty quickly. So some of the experimental facilities that we have, 2, 3, and 4-inch flow loops and experimental setup, test sections. We have sand erosion measurement equipment such as UV sensors and a lot of other stuff. We have gas and submerged liquid jet engagement test setups. We can test different materials, different conditions. We have PIV and PTV to measure fluid velocity and particle velocities. We also do have wire mesh sensors that I did not put in here. We have liquid droplet impact facility. We have tree cell erosion corrosion flow loop and sand and CO2 erosion corrosion flow loop. And these are some of the main flow loops that we have. To just show you some example pictures, we have a boom loop here that you're observing. We have 2 and 3-inch test sections. On the loop that we have here, we could go horizontal or vertical, depending on the geometry orientation you want to look at. Then we have elbows, test sections that we can get like any material we want to look at, and we put UT sensors on them to look at the thickness loss of the wall of these elbows under different conditions. So in temperature compensated conditions, we have these readings over a long period of time after the testing, so we can see what is happening inside the pipe, because I cannot cut it open every time, right? This is another experimental facility that we have. This is a 2-inch flow loop. You see we have like compressor, tank, we have pumps, we have a filter system when the slurry goes back into the tank. We have a 4-inch section, and we have some 2-inch sections up here. We have, that is metallic elbows. Some underneath PID PTV system, as I said, we mostly look at the particle impact velocities to know what exactly the impacting velocity of the particle is. There was an assumption before that the particles travel at the same speed of the gas or liquid. That is very false. So we started looking at this to look at that slip velocity. When we are interested in specific particle velocities, your gas velocity would be something else. So as you see here, we have a system, we have a laser sheet that is going to look at these particles that we are injecting in, from a compressor to a nozzle. We take pictures with a camera, we take consecutive pictures, and then we look at that to analyze our velocity field. And you see some sample pictures here that we have of the particles. Right. We also have a liquid droplet impact facility that we are currently building. This is actually a work by one of my PhD students. So we are mainly looking at droplet, liquid droplet erosion in wind turbine blades. But this is also applicable to pipelines, because that also happens with liquid droplets. So we're building this to have a standard way of testing different parameters and different factors. So this is the schematic that you see. We have a motor, we have a hub, we have 2 rod samples at 2 ends, and then we have droplets distributed on this falling down, so I can look at what happens to the sample or different material I'm looking at. So we have this like whole little room that we built. It is about 6 feet by 6 feet, and that contains all the system over here. This is the corrosion stuff. Would you like to talk about this?
So, at the Erosion Corrosion Research Center of the University of Tulsa, we have like 2 main testing facilities that we use for CO2 corrosion and erosion corrosion studies. Okay, the first one is the single test cell erosion corrosion flow loop and the 3-cell erosion corrosion flow loop. These flow loops are similar in design and operation, okay, and it's used for the same purpose. But the main difference between the two is that this flow loop can like have 1 test at a time, but in the 3-cell system we can run like three tests at the same time. For example, erosion, corrosion, and erosion corrosion. So this is the main difference between the 2 testing facilities. So here we can see a schematic of the single test cell erosion corrosion flow loop testing facility. Okay, so as we can see here, the main components of the testing facility including the tank that act as a source of the brine solution. Here we have a PA section where we can measure pH at the beginning, during, and at the end of the test. We have circulating pump, and then a bypass section where we can measure the flow rate. And then here we have like the test section. This section is having the single test cell where we put the samples, the steel and different material samples here. And as we can see here, this section is equipped with a cyclone separator. So the main purpose of using this cyclone separator is to keep solid particles flow through the section without flowing back into the tank and then going through the pump. Also, as you can see here, we have like the feeder or the injector. This is where we can introduce solid particles as well as chemical inhibitors into the system. And here, in the outer space here, we have the a dosing loop, okay? So it's an additional loop that is added into the main flow loop. So the main purpose of this dosing loop is to have to introduce either sodium hydroxide or sodium bicarbonate solution or hydrochloric acid solution to adjust the pH of the system. Here in this table we can see the parameters that we can do and also the capabilities of our testing, flow loop testing facilities. Okay, so for temperature we can go up to 200 degrees Fahrenheit, starting from 135 and then going to 200 degrees Fahrenheit. And then for pH, we can go from 4 to 7, and again we can adjust pH by adding hydrochloric acid, sodium hydroxide, or sodium bicarbonate solution by means of the dosing loop. Then for flow velocity, we can do up to 45 feet per second flow velocity, and now we are in the process of designing a new loop that is capable of doing even higher flow velocity that could go up to 100 feet per second probably. Okay, and then for the gas, we are using like CO2 gas and nitrogen gas. So for corrosion and erosion corrosion experiments, we use CO2 gas, and for pure erosion experiments, we do nitrogen gas, and we can go up to 150 psi for the pressure, for the gas partial pressure, and then for sodium chloride concentration, we can go from 1% to 20% by weight sodium chloride, and we derate our system by means of vacuum pumps, and we can claim that the oxygen concentration in the brine solution can go less than 10 parts per billion. The water cut, we can go from 40 to 100, and we use mineral oil as for the second phase, the second liquid phase. Corrosion inhibitors, just like different types and different concentrations we did and we can do. And for solid particles, so we have in the past we have used silica sand and calcium carbonate. And for the solid particle sizes, depending on the facility, so for example the 3-solid testing facility, we can go with very fine particles. And with the 1 cycle separator, we are limited for solid particles that are more than 50 micron. Then solid particle concentration in the range from 0.3 to 3% by weight. Two measurement techniques are used in these flow loop testing facilities, including the long-term weight loss method and the electrochemical linear polarization resistance technique. The geometry is the elbow and the plug T-test cells, okay, that are like normally used in our testing facilities. Tests that we have done and we are doing, including erosion corrosion, and inhibited corrosion. Right, so this concludes my part of the talk, and I will turn it over to Mike again. Thank you.
I promise this is the last time. So, why do we do all this work? Why do we look at all this experimental stuff? Why do we do all this modeling? And how do we present it to our members? We have developed four different softwares. They're very user-friendly. The first one is SPPS that I talked about, Sun Production Pipe Saver. The second one is CO2 Corrosion. It's called the Sweet Production Pipe Saver SPPS CO2 that Dr. Nelson was talking about. The third one is SPPS Erosion Corrosion for sand erosion and CO2 corrosion. And the last one is Liquid Impact Erosion Software or lies, but do not trust that acronym. The results are not lies. So, what are our membership benefits? All of our members can have access to all of the 4 user-friendly programs. The companies would benefit from 40 years of research. We used to have a lot more member companies. Right now we have about 16 or 17 members. With these numbers, each company pays only 1/40th of the cost, or 5%, but they get 100% of the result of the work that we do. We do meet twice a year to present all the results, all the research that is being worked on, and we upgrade our softwares, and we provide them with the upgraded SPPS software programs. So all of our members have access to all these results, all these upgrades and everything, as long as they are the member of the consortium. What are the costs? The costs are not that much for companies relatively. For the first year for joining, we do have a one-time equipment fee of $21K plus $32K a year. So first year is $52K, and each year after that is only $32K. This is to support our researchers, our students, and also for the equipment and maintenance and building the facilities and running the tests. So. Some of the current projects that we have at ECRC includes, but not limited to, looking at small particle corrosion for particles less than 50 microns. You would be surprised what those small particles can do. I can tell you all about it because that's where I did my PhD. Erosion multi-phase flow. We look at slug flow, angle flow, and low liquid cases. We do experiments in 3 and 4-inch pipes. We do various conditions, particle sizes. We work on development and improvement of erosion equations. We conduct erosion corrosion experiments that we talked about to validate and improve the models that we have. We are working on developing our SPPS 2D and extension of it to handle other geometries and flow conditions such as elbows, gradual contraction expansions, and same screens. In the near future, we're going to work on that. The effects of fluid viscosity on erosion, the effect of slurry concentration on erosion, and improvement of SPPS and SPPS erosion corrosion user-friendly computer programs based on the results that we get from different projects that our students are working on. Just to give you an idea of how many projects and how many students and research associates we have that their work is going into just SPPS. That's one of our softwares. We have improvement, one person working on improvement of SPPS 1D and 2D. We have the same person looking at development improvement of gradual contraction and expansion geometries. We are also having added an artificial intelligence module to our SPPS program. We look at CFD of larger diameter elbows and cushion tees in high pressure gas and liquids. We have an uncertainty model that we have developed for SPPS. We have liquid droplet erosion. We have erosion data for bend geometries, erosion data for scale-up liquid-dominated flows, for small particles and gas-dominated and multi-phase flows. We have elbows in series, liquid and gas-dominated flows, and improved erosion model accounting for particle size effects in liquids and erosion at low impact velocity and high temperature conditions that was supported by DOE. So all of this work that is conducted by our students and our research associates goes to these softwares, and all of our members have access to them. So at the end, I would like to acknowledge the support of the member companies of ECRC, major oil and gas and service companies from all around the world, and the project monitors since 1983. And the list is long, so I'm not going to read through it. So we would like to thank all of them for their great support. I would like to also thank the ECRC investigators, Dr. Siamak Shirazi and Dr. Michael Keller, the research associates, Dr. Sadras, Dr. Dariaki, Dr. Vieira, our technicians, and many master's and PhD students that we have had that work on this stuff. This concludes my part of the presentation. I really would like to thank you for your attention. I'm going to hand it over to Mike.
Thank you. So when you take a look at all the testing that TU does, you may know this or not, but we have a flow facility that we do a ton of flow development for specialty valves. And whether it's developing trim for control valves, whether it's a different seat design for ball valves, pipeline, any type of valves. And so our flow lab, we got 4 flow loops. We've got a liquid flow loop that goes up to 2,700 gallons a minute. We have an airflow loop that goes up to about 1,000 psi as well. And so we do, tank testing to all types of CV verification. You can never trust manufacturers out there in some cases for CVs for valves, so it's important to make sure you understand the pressure drop through your system. We look at pressure decay, like I said, working with the University of Tulsa, we understand what's going on with particles and sizes for trim configurations to make sure that your pipeline lasts a very long time from a flow control standpoint when you need to shut it off. One thing in our flow facility as well, we have a slurry loop, which we can measure basically the same conditions as some of the University of Tulsa, but just at a higher pressure with our system. So we have down here, here's my valve slide. So I'll be very familiar with what a trunnion valve looks like. I'll make this quick. Obviously, when you open and close the valve, when you're going through a picking process, that's when you have the scale and corrosion or erosion conditions happening around the valve, or it could happen around the seats of the valve, and you get the crud in there, which damages whether it's a normal trunnion mounted valve or slab gate. Any type of valve is going to have corrosion in the seat. And one thing, again, when you look at least COVID gave us the opportunity to look at things a little differently over the last 3 years. And so we developed some new capabilities. And like I said, we have a specific flush and cure system to help reseal a valve. It's not shutting off if you have to pig or shut off a pipeline with our system that's rolling out in 2023. So again, thank you guys for your time. Thanks for inviting us. And thanks for the great help by the University of Tulsa. We're glad to be here.